So we are up to section 8.4, which is the shape of the sampling distribution of the mean. So up until this point, we talked about the definition of the sampling distribution of the mean and how to calculate the mean and standard deviation of the sampling distribution of the mean, right? Mu sub x bar and sigma sub x bar. But now let's talk about shape. How do I know what the distribution looks like? Is the sampling distribution of the mean normal? Is it not normal? So we have two theorems. The first theorem doesn't have a name in this text. It's just called theorem 8.1. But the assumption is for theorem 8.1 is that if we sample, let's suppose we sample from a normal population, then the shape of the sampling distribution of the mean is also going to be normal, regardless of what size our sample is. So regardless of sample size n. So for a normal population, if we sample from a normal population, from a normal distribution, then the sampling distribution of the mean x bar is also going to follow a normal distribution, regardless of the sample size. And following are the characteristics of the sampling distribution of the mean when we sample from a normal population, whose mean is mu and whose standard deviation is sigma. So we said that the sampling distribution of the mean would be normal, regardless of sample size. We know that the mean of all the sample means is equal to mu, and the standard deviation of all the sample means is still equal to sigma divided by the square root of n. So that's theorem 8.1. And I'm going to show you guys a simulation in a minute that's going to illustrate this. And then we'll do some examples in the next lecture. But what if we sample from a non-normal population? So theorem 8.2, which has a specific name, the central limit theorem, and a lot of times I'm just going to call it CLT for short. So for any population, the sampling distribution of the mean approaches a normal distribution as sample size n becomes large. This is true regardless of shape of the population that's being sampled. So the general rule for applying the central limit theorem is the n greater than 30 rule. So for most applications, a sample size n greater than 30 is considered large enough to apply the central limit theorem. So the sampling distribution of the mean x bar can be approximated by a normal distribution whenever the sample size n is greater than 30. So this is assuming we're sampling, whoops, let me get my highlighter, from a non-normal population. So if we're sampling from a non-normal population, then the sampling distribution of the mean is approximately normal only if sample size is larger than 30. The mean of all the sample means, mu sub x bar, is still equal to mu, and the standard deviation of all the sample means is still equal to sigma divided by the square root of n. So before we get to these examples, let me show you a video that's going to illustrate these two concepts. I think rather than seeing, these formal definitions, a lot of times it's easy to understand when you see it being illustrated, right? So I have this video that's going to simulate the two different theorems that we're talking about here. So let me just share my screen.
So let's check out this cool simulation on the central limit theorem. So up here, this is then the population of all of our data. And down here, we're going to fill out then the sampling distribution. So what happens when we take a sample size of 2, take its mean and plot it? So here we take a sample size of 2. So those are our 2 observations. And then we have a mean of those 2 observations. Do this again. Take 2 more observations, then we have a mean of that one. And so our overall mean so far is 0. Keep going. We now have 3 different means of our 2 observations, and then our overall mean is 0. And then let's go ahead and do this then. Instead of I just did it 3 times, I took 3 different sample means. Now I'm going to take 10,000 sample means. And we can see that from a sample size of 2, so taking an observation from our population, 2 of them, taking the average and plotting them, that because our population is normally distributed, so will then be the sampling distribution of our sample means. It will also be normally distributed. Now let's go ahead and increase our sample size to, let's say, maybe 25, and you can mess around with this if you'd like. Still, we have a normal distribution for our population. Let's go ahead and animate the first one. So here we're taking 25 different observations. So that's n is equal to 25. And from that, then we get a sample mean, one sample mean. We plot it down here. Now do that again 10,000 times, and we can see that the distribution is still centered at the true mean, same as the population, but that the spread has become much less spread out. It's basically a factor of the square root of 25. However big my sample is, then the spread is going to get smaller by the square root of that. So this is one way that we can apply the central limit theorem. Now, something that's really interesting about the central limit theorem is that if we take a large enough sample size, we don't have to have this population to be normally distributed. So let's go ahead and change up this distribution. In fact, we can go to a custom distribution and we can actually create our own distribution. So let's say I create something like this. It looks really weird, right? So let's go ahead and take a sample size of 2 to start with. So pretty small. And let's animate that. So I've got 2 observations and a mean for that. Let's go ahead and do it again. I've got 2 more observations and a mean for that. Now let's go ahead and continue this simulation. So do that 10,000 times. And we can see that our distribution of sample means is not normal for a sample size of 2 from this wacky population distribution. And so what can we do? Well, according to the central limit theorem, if we take a large enough sample size, it doesn't matter what this looks like, it will become normally distributed as n increases. So let's go ahead and change this up to the largest sample size we can get. And let's see what we can do by just taking one sample of 25. So waiting for it to choose all of my observations from my large population, take a mean, and we plot it. So let's go ahead and do that again, but 10,000 times. And wow, look at that. Even though the population is distributed completely not normally, it's even bimodal, has some skewness, the sampling distribution becomes normally distributed. The mean is the same almost as the population mean, so really, really close. And the standard deviation is far less spread out. It comes in based upon how large of a sample size we've taken. So you can go ahead and play with this on your own. You can do a uniform distribution or a skewed distribution. I highly suggest that you check it out, and the link is below. I'll leave